Introduction. Units and measurements. Measurement of any physical quantity involves comparison with a certain basic arbitrarily chosen internationally accepted reference standard called unit. The result of a measurement of a physical quantity is expressed by a number or numerical measure accompanied by a unit. Although the number of physical quantities appears to be very large, we need only a limited number of units for expressing all the physical quantities, since they are interrelated with one another. The units for the fundamental or base quantities are called fundamental or base units. The units of all other physical quantities can be expressed as combinations of the base units. Such units obtained for the derived quantities are called derived units. A complete set of these units, both the base units and derived units, is known as the system of units.
Before we get on with the video, hit subscribe and press the bell icon next to it to get instant notifications of our latest uploads.
System of units. A complete set of units, both the fundamental units and derived units, is known as the system of units. In earlier time, scientists of different countries were using different systems of units for measurement. Three such systems are FPS, British System, CGS, Metric Absolute System, MKS, Metric Absolute System. Units for these three systems. Units: system, length, mass, time. FPS: foot, pound, second. CGS: centimeter, gram, second. MKS: meter, kilogram, second. SI system. The system of units, which is at present an international acceptance for measurement, is La Système International des Units. It abbreviated as SI. Uses of SI. As SI units of length and mass make use of decimal system, conversions within the system are simpler and more convenient. For international usage in scientific, technical, industrial, and commercial work, the SI units are widely used. Fundamental quantities in SI. Fundamental base quantity, unit, symbol. Length, meter, m. Mass, kilogram, kg. Time, second, s. Electric current, ampere, A. Thermodynamic temperature, Kelvin, K. Luminous intensity, candela, CD. Quantity of substance, mole, MOL. Supplementary fundamental quantities in SI. Plane angle, radian, rad. Solid angle, steradian, SR. Fundamental units and definition. In this module, we will discuss about definitions of fundamental units in SI. Meter, M. It is a unit of length. Let us see the path of light in a vacuum. Now we can define. The unit is the length of the path traveled by light in vacuum during a time interval of 1 by 299,792,458 of a second. Second, S. It is a unit of time. Let us see. There is cesium-133 atom. It is defined as the duration of 9,192,631,770 periods of two radiations, corresponding to the transition between two hyperfine levels of the cesium 133 atom. Kilogram, kg. It is a unit of mass. The kilogram is equal to the mass of the international prototype of the kilogram. Platinum, iridium alloy cylinder, kept at International Bureau of Weights and Measures at Sèvres, near Paris of France. Ampere, A. This is the unit of electric current. The ampere is that constant current which, if maintained in two straight parallel conductors of infinite length, of negligible circular cross-section, and placed 1 meter apart in vacuum, would produce between these conductors a force equal to 2 into 10 to the power minus 7 Newton per unit of length. Kelvin. This is the unit of the thermodynamic temperature. The Kelvin is the fraction 1 by 273.16 of the thermodynamic temperature of the triple point of water. Mole. This is the unit of quantity of substance. The mole is the amount of substance of a system which contains as many elementary entities as there are atoms in 0.012 kilograms of carbon. 12. Candela. The candela is the unit of luminous intensity. It is defined as in a given direction of a source that emits monochromatic radiation of frequency 540 into 10 to the power 12 Hertz, and that has a radiant intensity in that direction of 1 by 683 watt per steradian in that direction. Radian. Radian. Rad. This is the unit of plane angle. It is defined as the angle subtended at the center of a circle by an arc whose length is equal to the radius of the circle. Steradian. SR. This is the unit of solid angle. Steradian is defined as the solid angle subtended at the center of a sphere by its surface whose area is equal to the square of the radius of the sphere. Measurement of length. Different types of lengths are measured by using different types of instruments. Lengths like the length of cloth or length of a line can be measured by using measuring tape, a meter scale or a foot rule. But these instruments cannot be used to measure the diameter of a metal sphere or a cylinder. To measure the diameter of a cylinder, we can use paper strip method and wooden block method. Paper strip method. Wind the strip of paper closely around the object once and prick the overlapping position with a pin shown in figure. A method for measuring diameter of a cylinder. Unwind the paper strip and measure the distance between the two pinholes. This measure is the measure of the circumference, since circumference is equal to pi into diameter. Hence, now the diameter can be calculated. Wooden block method. Place the sphere or the cylinder between two blocks in contact with a ruler as shown in figure below. A simple method for measuring diameter of a sphere. Read the distance between the two blocks on the ruler accurately. The line of sight should be vertical. Measurement of mass. Mass is a basic property of matter. It does not depend on the temperature, pressure, or location of the object in space. The SI unit of mass is kilogram, kg. The prototypes of the International Standard Kilogram supplied by the International Bureau of Weights and Measures (BIPM) are available in many other laboratories of different countries. While dealing with atoms and molecules, the kilogram is an inconvenient unit. In this case, there is an important standard unit of mass called the Unified Atomic Mass Unit, U. which has been established for expressing the mass of atoms as one unified atomic mass unit, is equal to 1 AMU, is equal to 1 by 12th of the mass of an atom of carbon 12 isotope, including the mass of electrons, is equal to 1.66 into 10 power minus 27 kg. Mass of commonly available objects can be determined by a common balance like the one used in a grocery shop. Large masses in the universe, like planets, stars, etc., based on Newton's law of gravitation, can be measured by using gravitational method. For measurement of small masses of atomic or subatomic particles, etc., we make use of mass spectrograph, in which radius of the trajectory is proportional to the mass of a charged particle moving in uniform electric and magnetic field. Range of masses. The masses of the objects we come across in the universe vary over a very wide range. These may vary from tiny mass of the order of 10 power minus 30 kg of an electron to the huge mass of about 10 power 55 kg of the known universe. Measurement of time. Thus, just as length has units like kilometer, meter, centimeter, millimeter, etc., time also has units like year, month, day, hour, etc. Units measuring more time, 1,000 years. A millennium consists of 10 centuries. Each century consists of 100 years, and in the range we finally come to the second. 1 second is the smallest unit of time that we can see in clocks and watches by the clicking of the second's hand. In the past, when there were no clocks, people used water clocks, the hourglass, candle clocks, and the sundials. We must thank Galileo Galilei for replacing all these devices by clocks and watches. Some of them are so accurate that they are beyond our imagination. The pendulum that you see in wall clocks started this replacement, and Galileo was responsible for this. Galileo is considered to be the father of modern science. In 1583, he discovered that the time taken for a single oscillation of a pendulum of a given length is always constant. This paved the way for the use of pendulum for controlling the time element in the clocks. To measure any time interval, we need a clock. We now use an atomic standard of time, which is based on the periodic vibrations produced in a cesium atom. This is the basis of the cesium clock, sometimes called atomic clock, used in the national standards. Such standards are available in many laboratories. In the cesium atomic clock, the second is taken as the time needed for 9,192,631 second 770 vibrations of the radiation corresponding to the transition between the two hyperfine levels of the ground state of cesium 133 atom. The vibrations of the cesium atom regulate the rate of this cesium atomic clock, just as the vibrations of a balance wheel regulates an ordinary wristwatch, or the vibrations of a small quartz crystal regulate a quartz wristwatch. The cesium atomic clocks are very accurate. In principle, they provide portable standards. The national standard of time interval second, as well as the frequency, is maintained through 4 cesium atomic clocks. A cesium atomic clock is used at the National Physical Laboratory (NPL), New Delhi, to maintain the Indian Standard of Time. Accuracy and precision. In our daily life, we do a lot of activities like purchasing different items, weighting different quantities, taking measures of different lengths, etc. But who knows whether they are accurate and precise? So let us start learning what is accuracy and precision. Accuracy is defined as the closeness of the measured value to the true value. Accuracy refers to quality of the measuring instrument as compared with the standard for that measurement. Precision is a measure of how closely individual measurements agree with one another, or is an indication of how much error can be expected in a measurement. Example: let us consider the measurement of length of an object by a meter scale. First, let us use a scale that is graduated in centimeters only. The end of the object lies between 4 centimeter and 5 centimeter markings. Making an estimation with our eye, we have recorded the length as 4.4 centimeter. But there is chance that it can be estimated as either 4.3 centimeter or 4.5 centimeter. The error due to eye estimation is 0.1 centimeter. Next, let us use a scale that is graduated in millimeters. The end of the object lies between 4.4 centimeter and 4.5 centimeter markings. Making an estimation with our eye, we have recorded the length as 4.45 centimeter. It can be estimated as 4.44 centimeter or 4.46 centimeter. Now the error is 0.01 centimeter. The second measurement, 4.45 centimeter, is more precise than first measurement, 4.4 centimeter. We can increase the precision by using vernier calipers and screw gauge. Definition: precision is a measure of how closely individual measurements agree with one another, or is an indication of how much error can be expected in a measurement. Accuracy. Accuracy is the difference between measured value and standard value or true value of an object. Suppose that the actual or true length of the object is 4.2 centimeter. The first measurement is 4.4 centimeter and the second measurement is 4.45 centimeter. Here, the measured value 4.4 centimeter is nearer to the true value of 4.2 centimeter. Therefore, the first measurement is 4.4 centimeter is more accurate than the second measurement, that is 4.45 centimeter. In other words, accuracy is the difference between measured value and standard value of the length of an object. Thus, the second measurement is more precise but less accurate. A measurement can be less accurate though more precise. Let us see an example. See the target board and someone hitting it with arrows. There are different kinds of possibilities in hitting the target. From this example, we can observe that Mark 1, poor accuracy, poor precision. Mark 2, good precision, poor accuracy. And Mark 3, good accuracy, poor precision. Mark 4, good accuracy, good precision. Systematic errors. The systematic errors are those errors that tend to be in one direction, either positive or negative. Some of the sources of systematic errors are 1. Instrumental errors, 2. Imperfection for experimental technique or procedure, and 3. Personal errors. Instrumental errors. Errors that arise from the errors due to imperfect design or calibration of measuring instrument are called instrumental errors. For example, in a vernier calipers, the zero mark of vernier scale may not coincide to the zero mark of the main scale, or simply an ordinary meter scale may be worn off at one end. Imperfection for experimental technique or procedure. For example, to determine the temperature of a human body, the thermometer placed under the armpit will always give a temperature lower than the actual value of the body temperature. Personal errors that arise due to the individual's bias, lack of proper setting of the apparatus of individuals, carelessness in taking observations without taking proper precautions, etc. For example, if you by habit always hold your head a bit too far to the right while reading the position of a needle on the scale, you will introduce an error due to parallax. Least count error. The least count error is the error associated with the resolution of the instrument. For example, a vernier calipers has a least count as 0.001 centimeter. It occurs with both systematic and random errors. The smallest division on the scale of the measuring instrument is called its least count. Systematic errors can be minimized by improving experimental techniques, selecting better instruments, and removing personal bias as far as possible. Random errors are minimized by repeating the observations several times and taking the arithmetic mean of all the observations. The mean value would be very close to the true value of the measured quantity. Absolute error. In this module, we will discuss about absolute error. The magnitude of the difference between the individual measurement and the true value of the quantity is called the absolute error of the measurement. Let us take the values of the length of rod with scale, measure its length 10 times and record it. The values are 9.2 centimeter, 9.1 centimeter, 9.2 centimeter, 9.25 centimeter, 9.15 centimeter, 9.3 centimeter, 9.05 centimeter, 9.35 centimeter, 9.25 centimeter, and 9.0 centimeter. Mean value of the length, A mean, is equal to 9.18 centimeter. Therefore, the true value of the length of a rod is 9.18 centimeter. Because mean value of the length of rod is equal to the true value of the length of a rod. True value is equal to 9.18 centimeter. Take one measured value is equal to 9.25 centimeter. Absolute error is equal to modulus of true value minus measured value. Therefore, absolute error is equal to A mean minus AI, or A1 is equal to 9.18 minus 9.2, that is equal to 0.02. The absolute error is always positive. It has same units as that of the quantity measured. Mean absolute error. Definition. The arithmetic mean of all the absolute errors is considered as the mean absolute error of final absolute error of the value of the physical quantity concerned. Take some observations. The length values 9.2 centimeter, 9.1 centimeter, 9.2 centimeter, 9.25 centimeter, 9.15 centimeter, 9.3 centimeter, 9.5 centimeter, and 9.35 centimeter, 9.25 centimeter, 9.0 centimeter. Find absolute error of each observation. Mean value of the length, A mean, is equal to 9.18 centimeter. Now, find the absolute error of the each observations are 0.02, 0.08, 0.02, 0.07, 0.03, 0.12, 0.13, 0.17, 0.18. Delta A mean is equal to 0.02 plus 0.08 plus 0.02 plus 0.07 plus 0.03 plus 0.12 plus 0.13 plus 0.17 plus 0.18 by 10, that is equal to 0.09. This mean absolute error is always positive and has the same units as the physical quantity measured. Relative error. The relative or proportional error of a measured physical quantity is the ratio of the mean absolute error, delta A mean, to the measure value, A mean, of the quantity measured. Relative error is equal to delta A mean by A mean. The relative error is a pure number having no units. A knowledge of the relative error is more important than that of the mean absolute error. Combination of errors. In this module, we learn about combination of errors. If we do an experiment involving several measurements, we must know how the errors in all the measurements combine. For example, density is obtained by dividing mass m by the volume V of the substance. D is equal to m by V. For this, we have to determine the mass of the substance m with a balance and the volume of the substance V with volumetric flask. All the measuring instruments as well as the measurements may have error. If we have errors in the measurement of mass and volume, we must know what is the error in density of the substance. Therefore, we have to know how the error in individual measurements m, v combine together and propagate in density error. That is, we want to know how the error propagates in sum, difference, product, and a division of quantities. Significant figures. Definition. The digits of a number represent a measurement that are definitely known, quite reliable, plus one more digit added at end, that is estimated, are called significant digits or significant figures. For example, the length of rod is equal to 4.3 centimeter. Here, the digit 4 is reliable, that is a clear marking on the scale. The digit 3 is an estimation added at the end. Now, measure the length of rod with a scale graduated in millimeter. In this case, the length of rod is 4.36 centimeter. Here, the digits 3 and 4 are reliable digits, but the digit 6 is an estimation. The last digit, estimated digit, should not be ignored because it gives some information about the measurement. Rules for determining the number of significant figures. Rule 1. The digits other than 0 are always significant. For example, 362 has 3 significant digits, 36.71 has 4 significant digits. 3.5 has 2 significant digits. Rule 2. Any final zero or zeros used after decimal point are significant. Here, the number 3.7600 has 2 final zeros. Then it has 5 significant digits. Rule 3. Zeros between two other significant digits are always significant. For example, consider a number 3.0078. It has 2 zeros between 2 significant digits, so they are also significant. Therefore, 3.0078 has 5 significant digits. Rule 4. 1. Zeros used individually for the decimal point are not significant, or all the zeros to the right side of the decimal point but to the left of the first non-zero are not significant. Consider a number 0.00689. It has 3 significant digits. 2. All zeros to the right of a decimal point are significant even if they are not followed by non-zero digit. Here, the number 8.00 contains 5 significant digits. 3. Zeros to the right of the last non-zero digit after the decimal point are significant. For example, the number 0.07200 has 4 significant digits. 4. Zeros to the right of the last non-zero digit in a number having no decimal point are not significant. Here, the number 3040 has 3 significant digits, as 0 after 4 is not significant. In this module, we shall discuss about rounding of numbers. Definition: the process of omitting the non-significant digits and retaining only the desired number of significant digits, incorporating the required modifications to the last significant digit, is called rounding of the number. In this example, 1.23557 is rounded off to 3 significant figures as 1.24. Procedure for rounding of numbers. Rule 1. If the last digit is less than 5, that can be ignored. For example, we have a number 2.721. Here, last digit 1 is less than 5, hence omitted. So, we can rounding off the number to 2.72. Rule 2. If the last digit is more than 5, the preceding digit must be raised by 1 and the last digit is to be omitted. For example, we have a number 26.248. Here, the last digit 8 is more than 5. Hence, 4 is raised by 1 and the last digit 8 is omitted. Hence, rounding off the number to 26.25. Rule 3. When the last digit is exactly 5 and if the preceding digit is even, then it should not be changed and the last digit 5 must be dropped. For example, see the number 27.265. 5 is dropped as last digit is exactly 5 and preceding digit is even. Hence, rounding off the number to 27.26. Scientific notation. In this notation, a number is expressed with the decimal point just after the non-zero digit and then multiplied by some power of 10. For example, let us consider a number 12,600. This number can be written as 1.26 into 10,000. And the number is expressed as in scientific notation 1.26 into 10 to the power 4. This is rounding off to 1.3 into 10 to the power of 4. Dimensions and dimensional formulae. In this module, we shall discuss about dimensions and dimensional formulae. The dimensions of a physical quantity are powers, exponent, to which the fundamental base quantities are raised to represent that physical quantity. For example, area is equal to L square. Density is equal to m by L cube. The dimensions of the fundamental units, mass, length and time, indicated by the symbols m, L and t respectively. If a derived unit has the nth power of fundamental unit, it is said to be of n dimension in that unit. If a physical quantity x involves all the three fundamental units m, L and t with powers a, b and c, then we may write physical quantity x is equal to m to the power a, L to the power b, t to the power c. This is called dimension formula. The dimension of various quantities can be written as follows. Area is equal to length into breadth. As length and breadth are measured in units of length, that is, area is equal to L into L. Therefore, the dimension formula of area is L square. Volume is equal to length into breadth into height. As length, breadth and height are measured in units of length, that is, volume is equal to L into L into L. Therefore, the dimension formula of volume is L cube. Velocity is equal to length by time. The dimensions of velocity are L by t or Lt to the power minus 1. Angle, ratio of arc by radius. Dimensions are L by L or principle of homogeneity of dimensions. In this module, we discuss about principle of homogeneity of dimensions. Let us consider a dimensional equation C is equal to A plus B. The terms on both sides of a dimensional equation should have same dimensions. This is called homogeneity of dimensions. For example, take the equation F is equal to MA. Writing in the dimensional form, we get the dimensions for M, L and T as both sides are equal as MLT power minus 2. This is the principle of homogeneity of dimensions. Identical dimensional formula. Two or more physical quantities may have the same dimensional formula. Some physical quantities with identical dimensional formula. 1. Pressure, stress, elastic moduli have same dimensional formula, that is, ml power minus 1, t power minus 2. 2. Wave number, focal power, Rydberg's constant have same dimensional formula, L power minus 1. 3. Work, energy, torque, moment of couple have same dimensional formula, ml square, t power minus 2. Dimensional formula are used along with the principle of homogeneity of dimensions. Applications of dimensional method of analysis. Let us discuss some applications of dimensional method of analysis. 1. Transformation of units of measurement. 2. Check the correctness of equation. 3. Derive relationship between different physical quantities. Convert one system of units into another system. Let the dimensional formula of physical quantity be m power a, l power b, t power c. Let n1 be its numerical value in one system in which unit of fundamental quantities are m1, l1 and t1. Then the numerical value n2 in another system in which unit of fundamental quantities are m2, l2 and t2 is given by n2 into m2 power a, l2 power b, t2 power c is equal to n1 into m1 power a, l1 power b, t1 power c. Therefore, n2 is equal to n1 into m1 by m2 power a, l1 by l2 power b, t1 by t2 power c. As an example, let us find relation between units of energy. Joule is the unit of energy in SI and erg is the unit in CGS system. Dimensional formula of energy is m power 1, l power 2, t power minus 2. Let 1 joule is equal to n erg. N is equal to 1 joule per ergs. Hence, therefore, N is equal to m1 by m2, l1 by l2 power 2, t1 by t2 power minus 2. As unit of ml and t are kilograms, meters and seconds in SI system, and grams, centimeters and seconds in CGS system. N is equal to 1 kg by 1 gram into 1 meter by 1 centimeter power 2, 1 second by 1 second power minus 2. N is equal to 1000 grams by 1 gram into 100 centimeters by 1 centimeter power 2, 1 second by 1 second power minus 2. N is equal to 1000 into 100 square into 1 square. N is equal to 10 cube into 10 power 4 is equal to 10 power 7. Therefore, N is equal to 10 power 7. 1 joule is equal to 10 power 7 ergs. To check the correctness of equation. The correctness of an equation is verified using the principle of homogeneity of dimensions. This principle that terms on both sides of a dimensional equation should have same dimensions. Let us consider the equation t is equal to 2 pi square root of L by G and check whether it is correct or not. We know dimensional formula of T, L and G are T, L, LT power minus 2 respectively. Therefore, dimensional formula of square root of L by G is equal to square root of L by LT power minus 2 is equal to square root of T square is equal to T. Dimensional formula of left hand side is also T. As 2 pi is a dimensionless quantity, the dimensional formula of left hand side of the equation is equal to dimensional formula of right hand side. Hence, we conclude that the given equation is a correct one. To derive the relationship between different physical quantities, let us derive an expression for the velocity of sound in solids. Let v be the velocity of sound in a solid. Assuming that the velocity depends upon the velocity d and the coefficient of elasticity E of the medium, we have let v directly proportional to e power a and v directly proportional to d power b. A and b are constants. V is equal to k e power a d power b, where k is the proportionality constant. Dimensional formula of v, e and d are: v gives rise to m power 0, lt power minus 1. E gives rise to ml power minus 1, t power minus 2. D gives rise to ml power minus 3, t power 0. As k has dimension.
इस चैनल को लाइक कीजिए, सब्सक्राइब कीजिए और सबको इसके बारे में बताइए।